Good afternoon, everyone. My name is Stuart Grant. I'm a third-year PhD student at the University of California, San Diego. Today I'm going to be presenting some work I did with my advisor, Alex Snoren, called In-network Contention Resolution for Disaggregated Memory. And so resource disaggregation is an architecture in which you have resources like CPU, memory disk, and accelerators, each of which is separated over a network. And one of the biggest tricks in getting this architecture to work is the fact that there's additional latency incurred whenever you want to access any one of these resources. And nowhere is that truer than with regards to local versus remote memory, where the cost is approximately 20x, with a local cost being around 50 nanoseconds and remote being in the best case around 1 microsecond. And so the question that we're going to be exploring here is, can we use the network which interconnects all of these resources to improve the performance of systems built with resource disaggregation as an architectural assumption? There's a number of different projects in this space that have different techniques for managing remote memory. A lot of them use RDMA, and that's what we're going to be talking about today. They're typically optimized for high throughput, low latency, and a number of which overlay remote memory with these highly optimized data structures. Traditionally, the assumption is that end hosts have NICs with RDMA primitives that they use to gate access. And also, built into most of these is the assumption that there's a CPU on the remote server which can be used to serialize access to its remote memory. And so even if the CPU isn't necessarily participating in a lot of the computational tasks traditionally associated with something like an RPC, it'll still be there to serialize access. And so if you look at the table on the right, we have projects like Farm, Herd, ERPC, Storm, even like OS, all of which operate under the assumption that there's a remote CPU. There's a few projects which work under the alternative assumption of passive remote memory. And so remote regions, Clover, both of which assume that there is no CPU co-located with remote memory. And the downside here is that they do not have a CPU to coordinate access. So what's the cost? Well, the cost comes in the form of contention, because rather than having a remote CPU perform serializations, the clients do it. So when they perform a read or a write, they need to somehow self-organize in a way that allows them to perform consistent writes. But they can't do this alone. They don't have the ability because it's naturally distributed and naturally concurrent. And so what happens when you make this disaggregated assumption? Well, when resources are contended, it leads to a performance loss. And what you see on the right here is a chart that I've collected from results posted in Clover where the writes are increased. Using the YCSB benchmark, which has, under the C definition, 0% writes, B is 5% writes, and A is 50% writes. And what you see is that a 50% read-write ratio, Clover's performance drops to 5x. And this is in the face of them having a very smart algorithm which opportunistically allows the writes to succeed in an O of 1 case. What you're seeing here is that there are hotkeys in this key value store, and when they're contested, there's a protocol that repairs the writes so that they're consistent, but it's costly. And so that is the nature of why there's performance degradation here, is contention. Now, the thing is that all these operations are serialized in the network anyways. Under the assumption that this is operating at rack scale, once these RDMA operations flow between clients through a TOR, by the point that they hit the egress port on the switch, they're serialized operations because only one packet is being delivered at a time. And so from the TOR's perspective, these RDMA reads and writes are executing very similar to how a single threaded program would observe them. And so again, the question that we're asking here is, given now that we understand that this naturally concurrent RDMA read-write from multiple clients is serialized, how can we use this knowledge in network to improve performance? There's a number of challenges here, and the first of which is that switches are not necessarily intended to participate in any sort of key value protocol. They're intended for packet forwarding. And the moment that you start to integrate this into an algorithm, you start to hit very hard limitations, such as the fact that switches have just a little bit of SRAM on them, and it's at a premium because it's usually used for packet buffering. Also, the integration of a switch into a system increases the risk of failure. So anything that you put on there, you don't necessarily want to be an integral component because it could lead to cascading failures. And also it has a restrictive programming model. So programmable switches, as of yet, only operate on P4, which is a match action pipeline, which doesn't give you the full programmable flexibility of a CPU. Also, there's no RDMA connections. So the other approaches for this would be to do something like have a middle box which has RDMA connections to the server and the client and could potentially order them. But in the case of using a switch, the only thing that you get to see is in-flight packets. So I have an example here that demonstrates what one of these conflicts looks like and how it can be observed and potentially fixed using a top-of-rack switch. And so this is a write conflict in which values are being appended to a list concurrently. And it just so happens that this is exactly the algorithm that occurs inside of Clover. And so using this example, we'll explain some of the improvements that we've made. And so here we have the head of a list on a remote memory server. It has two values, the first of which is a pointer to potentially next values, and then it just has its storage. Now, both of these clients are going to do two operations, the first of which is to write to a safe partitioned space, and then they're going to commit their writes to the chain. And so this first write operation can happen completely concurrently. There's no conflicts. So client A is going to write to location 1, B is going to write to location 2. Now, in the second step, they're going to actually add these values to the end of the list. And so in this case, just naturally concurrently, A is going to win. It's going to run an RDMA compare and swap, which is like an atomic lock. Make sure that the value is what you assume it is, write it, do that atomically, and then return. And so it's writing under the assumption that it's at the tail of the list, so it should see null. It succeeds, the pointer is written, and this remote structure has a new tail. Now B is going to write afterwards. And its assumptions are broken here because, again, it hasn't learned that this update has occurred. And so it's going to run the same compare and swap. It's going to try to put its own value, 02, at the end. And it's going to fail because instead of finding null, instead of finding the tail of the list, it just finds the value that A wrote. And so it's going to fail. And what does it have to do in this case? Well, if there was a CPU on the memory server, it could, fix this for it potentially, but there's not. So B is going to have to do a number of things. It's going to have to do what is known as pointer chasing, which is that it's going to read the new value, then it's going to traverse using that new virtual address on the remote server, then it's going to try again. So 3 round trips just to actually commit its write to the tail. This is the nature of the contention that we're addressing. And this is the reason that the performance is failing in the other case. And the question, again, is how can we use the network to speed this up? So looking at the same example again, but this time we've got an algorithm that we've written which caches some metadata about this list on the TOR. And so specifically, we're just going to keep the tail cached and the locations of writes that haven't been committed. So the tail is 0x00, and outstanding is nothing because we haven't written anything yet. But going forward, just like we did before, the first 2 writes commit, they are added to the outstanding list. So this is just a small amount of cached metadata so that the TOR can keep track of what has been written. Now in the next case, the client performs its compare and swap again, exactly as before, except now the cache updates itself. So it knows that the tail has moved. It removes 0x01 from the outstanding list, and the algorithm proceeds. Okay, here's where the magic happens. Well, client B issues its same compare and swap, again, pointing at 0, and assuming that it's going to be appending from the root. But again, it's late. This time, however, when it reaches the Tor can tell that it's targeting the wrong location because it knows that it's not writing to the tail anymore. And so this is the true manipulation. So in flight, the Tor can check that the virtual address in the RDMA packet is not pointed to the correct location. It can update the RDMA packet in flight. It's going to do RDMA specific things like recalculate its invariant CRC, and then it's going to steer its virtual address to the correct location. And so without needing to do multiple round trips, it's just going to succeed. And so this is the nature of our fix, is that we've cached a small amount of metadata on a Tor, and then we use it to deal with write conflicts in the data path. And so as a proof of concept, we've instrumented Clover. We have interposed on Clover. We cache tail pointer per every key because that's the way that this algorithm works. And whenever write conflicts occur, we modify the RDMA packets in flight so that they all succeed. And so as a preliminary evaluation for our technique, we want to test, first of all, do we get a throughput improvement? That's the most important thing. And then afterwards, as we said before, switches are not really built to do a lot of heavy lifting computationally. And so we want to make sure that both our computational footprint and our memory footprint are relatively small. Our setup, we don't actually use a P4 switch. We use a DPDK program that acts as one for us. We have a 100 gigabit Onyx Tor switch, which forwards packets from Clover to ours, and it just acts as an interposition layer without making any modifications to Clover. And all of this is running on ConnectX 5 NICs at 100 gigabit per second. And so again, the first question is under write contention, what we saw before, so YSCBA, 50% read, 50% write, what is our performance going to look like relative to the baseline? And in this case, we have 2 client machines, each of which has 32 cores. Okay, and so what you can see here is a comparison between Clover, which is in red, which is our baseline, and write redirections, which is our algorithm, in blue. On the vertical axis, you see the thousands of operations per second, which are committed, and along the x-axis is the number of threads that are participating in this individual run. And what you can see is that at 2 threads, there's a small amount of contention, and we come out ahead there by a small margin. But after 32 threads, we really start to pull away. And this is where the number of conflicts starts to increase to a point at which it's significant. And so here at 64 threads, we see improvements of roughly 1.4x. As I mentioned before, this is a memory constrained system. And so what I have on the right here is a graphic of how much space our technique uses as a proportion of the key space. And I've marked it with a line to show how much memory is on a barefoot Tofino 2. And so up to about 250K keys, this will all fit. But at that point, you're already starting to reach over a megabyte or near a megabyte. And that is where you're going to start interfering with data or memory, which is really intended for packet forwarding, and we don't want to do that. So the question becomes, how many keys do we need to store, and what sort of performance boost are we going to get out of having a certain number of the keys cached? So we ran another throughput experiment, and this time we only cached a small proportion of the keys. And the keys that we cache start in the most contested order. So if we're caching 1 key, it's the most contested. And this is a ZipF distribution, so key 1 is by far the hardest hit. And that's what you're seeing in this graph on the right as we increase the number of cached keys across the x-axis, is that even adding the top 8 most contested keys, sees a relatively high improvement in the throughput. It's specifically at 8 keys, which is only 128 bytes, we're seeing an improvement of 1.3x. And this increases all the way up to 128, where we see our value that we showed before of 1.4. And so that's relatively interesting. I mean, we managed to get a performance boost using relatively small amounts of memory. And the question is, where can we go from here? Well, one of the biggest drawbacks that we've seen so far is the use of these compare and swap operations. They're very expensive. It's been documented in other literature. And the question is, given that we know that they're expensive and given that we have serialized ordering on the Tor, is there any way that we can potentially remove or re-architect systems which have this passive memory assumption to not use compare and swap as atomic operation? And there's a few ways we've thought about doing this. One option is to try to use ordering on the NICs themselves, so taking all the requests that might conflict and sending them to the same queue pairs. The other option, which we've considered, is replacing compare and swaps with traditional writes under the assumption, again, that we know their ordering. So given serialized access, it's not necessarily required that we use a lock. So we might be able to see some performance boosts there. Another question is about generality. And so we showed that this works on a single data structure with relatively simple operations, append to the end of a list. And we believe that the generality of our technique hinges on the complexity of the invariants which these data structures require to keep their structure. And so something like an ordered list would be more difficult to maintain and require more state on the switch than something that only requires us to keep a tail. And one of the last questions is about scalability. And we demonstrated our technique on a switch, but we could potentially do this on SmartNICs as well, under the assumption that we don't need to order requests across multiple hosts. Thank you for listening. We've demonstrated today that there's significant performance improvements to be had by centralizing and serializing in the network, at least for RDMA systems with write contention. Again, my name is Stuart Grant. I've posted my personal page and the repository of our code here, and I'm happy to answer any questions that you have. Thank you.